Hello, welcome to this 43-minute supplement on Newtonian orbits for the Gravitation and Black Holes course. The lecture script for all the supplemental videos is available at a link given in the description of this video. We will cover elliptical orbits, Kepler's laws, orbiting the Sun, orbiting the Earth, effective potential energy, orbital maneuvers, Hohmann transfer orbit from Earth to Mars, and perturbation of orbits, and precession of perihelia. We will look at Newtonian elliptical orbits, primarily around the Sun. The next supplementary video, number 6, will look at the general relativity case and orbiting a black hole. Circular orbits are a special case of elliptical orbits. The planetary orbits in our solar system are very nearly circular. We could just treat circular orbits, but we also want to know how to rocket from Earth to Mars efficiently, and that requires an elliptical orbit. So we will treat elliptical orbits and realize that circular is a special case. We will focus on two objects with mass in closed gravitational orbit with one another. The objects may be spinning. Spin has no effect on orbits for the Newtonian case. We assume the objects are electrically neutral. The objects are spherically symmetrical mass distributions, so we can treat them as point masses, but feel free to think of Earth orbiting the Sun. The objects are moving in vacuum, so no friction, no viscous force from gas. We will not treat tidal acceleration and tidal locking in this video. Just the simplest case of two bodies. Adding a third body adds complications. In our case, energy and angular momentum are conserved, and a closed bound orbit is a stable, repeating orbit in a fixed plane. These need not be so for two bodies in general relativity. As shown in this diagram, an ellipse has two focus points or foci, the green dot and the orange dot. The ellipse is the set of all points, the green curve, for which the sum of the distances to the two foci is a constant. So the distance r plus distance r sub 2 is constant, being twice the a, the semi-major axis length, from here to here. B is the semi-minor axis length, from here to here. Epsilon is the eccentricity from 0 to 1 of the given ellipse. Let two objects of mass capital M, red, and lowercase m, green, orbit one another in an elliptical orbit. This can be separated as each orbiting their common center of mass. The center of mass is here, with the same orbital period as one another and in synchronicity with one another, such that the line between their centers always passes through the center of mass. So here it passes through the center of mass, here it passes through the center of mass, here it passes through the center of mass. For this particular diagram, I've chosen the smaller mass to be 1/4 of the larger mass. The center of mass is the focus for both bodies' elliptical orbits. It's the focus for this red orbit, and it's the focus for this green orbit. For simplicity, we will treat the case where one mass is much more than the other mass, like the Sun and the Earth, in which case the center of mass is close to the center of the more massive object, so we wouldn't even see this red ellipse. And we're only interested in the orbit of the lighter mass. The lighter mass orbits the center of mass, but this is very nearly the center of the more massive object. Prior to Newton, Kepler contradicted Ptolemy and identified 3 empirical laws of planetary motion based on astronomical observational data. The orbit of a planet is an ellipse with the Sun at one focus of the ellipse. Kepler discovered that orbits are ellipses, not circles, by analyzing the data from Mars's orbit, whose eccentricity is larger than for Venus, Earth, Jupiter, or Saturn. Actually, the focus of the planetary orbits is at the center of mass of the solar system, which is slightly outside of the Sun due to Jupiter's mass and distance. A line segment joining a planet and the focus at the Sun sweeps out equal areas during equal intervals of time. So the time it takes to go from here to here is the same time it takes to go from here to here. The areas are the same. The velocity here is less than the velocity here. Sweeping out equal areas in equal times is a consequence of angular momentum being constant, as Newton discovers. A planet's orbital angular velocity is highest at its closest approach to the Sun, called perihelion, and lowest at its furthest distance from the Sun, called aphelion. The square of a planet's orbital period, t, capital T, is proportional to the cube of the length of the semi-major axis, lowercase a, of its orbit. Here's the period squared, and it's proportional to the semi-major axis a cubed. This is the correct expression for one single body orbiting another larger body. When the mass of the more massive object is much larger than the smaller mass, then this denominator is very close to gm, capital G, capital M, and so becomes nearly independent of the smaller mass. And so the period squared becomes proportional to the semi-major axis cubed without regard for the smaller mass. It takes a bit of work to prove this formula using Newtonian mechanics, which we won't do here. Orbiting the Sun. Orbiting the Sun. For orbiting the Sun, the period divided by 1 year squared is equal to the semi-major axis divided by 1 astronomical unit cubed, because Earth's orbit at distance 1 astronomical unit has a period of 1 year. Inner planets have shorter periods than more distant planets do. In this diagram, the horizontal axis, this is a log-log diagram. The horizontal axis is semi-major axis of the planets, and the vertical axis is orbital period in Earth years. Mercury is in closest and has a period of a quarter of a year. Next comes Venus, and its period is almost 2/3 of a year. Earth, 1 year. Mars, 1.88 years, and so on. And this green line represents this Kepler law for the solar system. And it applies whether the planet is very massive or not. A body orbiting at 4 times Earth's orbit between the asteroid belt and Jupiter would have a period of 8 years. 2, 3, 4, 8 years. A body orbiting at 9 times Earth's orbit, a little closer than Saturn, would have a period of 27 years. A body orbiting at 100 times Earth's orbit has a period of 1,000 years. Beyond the orbit of Neptune, the Kuiper belt extends from 30 to 50 astronomical units, with periods of 60 to 350 years. Many comets are Kuiper belt objects. They spend most of their time out beyond Neptune and a very small amount of their time closer into the Sun. So on this diagram, here's Neptune. Kuiper belt would be in this region, and beyond the Kuiper belt, there's the Oort cloud. It extends from 2,000 to 200,000 astronomical units. And these Oort cloud objects have periods of 30,000 to 90 million years. And some of the comets that come close to the Sun are Oort cloud objects. Now, Alpha Centauri here is a nearby star. Don't be confused. This horizontal scale is a log scale, so it's not really close to the Oort cloud because there's so much distance here. For orbiting the Earth, the period of orbiting objects is about 84 minutes times their semi-major axis divided by the radius of the Earth to the 3/2 power for orbiting the Earth. For the International Space Station at altitude 420 kilometers, the orbital period is 93 minutes. Equatorial geostationary orbits with a distance to Earth's center of 6.6 Earth radii have an orbital period equal to 1 day, so the satellite remains at a fixed longitude. The Moon's orbital period is 27.3 days at 60 Earth radii. It was gratifying to Newton that his mechanics and law of universal gravitation explained the Moon's orbit as well as the fall of an apple on Earth. Relative to straight-line motion, the Moon is falling, accelerating toward the Earth at 3 millimeters per second squared. And this falling maintains its nearly circular orbit, while the falling apple hits the ground. Intercontinental ballistic missile, ICBM trajectories, they're ellipses that are suborbital, meaning that their closest distance to the center of the Earth is less than the Earth's radius. Green is the Earth's radius, black and red is the suborbital elliptical orbit. And this means that they will impact the Earth. If we launch it here and it has this elliptical orbit, it's going to hit the Earth here. Travel time between the US and Russia is 30 minutes or less. Thus the following Cold War humor of worldwide delivery in 30 minutes or less. I include this not to treat nuclear war as funny, but to make the 30-minute time memorable. As of 2021, the space tourism flights of Blue Origin and Virgin Galactic spacecraft were suborbital. Effective potential energy. Gravitational attraction is a conservative force, meaning that we can find an expression for the energy of the system that depends only on the positions of the bodies, or, in this case, the separation between their centers, which we'll use lowercase r. For a small spherical object of mass lowercase m orbiting a much more massive spherical object of mass capital M, much larger than lowercase m, with angular momentum of capital L, we have this effective potential energy. Effective potential energy as a function of distance is minus gmm over r plus L squared over 2 mu r squared, where mu is the reduced mass, capital M little m over capital M plus little m, and when capital M is much larger than little m, the reduced mass is nearly little m. And that's the case that we're going to be interested in. Angular momentum is distance times mass times tangential velocity. In the graph on the left, the black and green curves are effective potential energy, Newtonian. The horizontal axis is radius divided by surface radius, and it ranges from 1 to 20 here. So the horizontal axis doesn't go all the way to 1, it goes doesn't go all the way to 0, it goes to 1. The vertical axis is the effective potential energy divided by the potential energy at the surface of the larger object. So U effective over gmm divided by r surface. The black curve is for zero angular momentum, so we would use that if we were plunging radially. So plunge, 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 and then we hit the surface. Whack. The green curves have fixed orbital angular momentum, increasing from the minimum orbital angular momentum for the lowest green curve. So this would be an object that was orbiting just slightly higher than the surface. Each of these green curves has a minimum in the curve. You could see a minimum, a minimum, a minimum. Each of those minima is the circular orbit for that green curve, for that angular momentum. The red dot is the circular orbit for that particular angular momentum curve. The red dot on the left corresponds to the red circular orbit in the diagram on the right. The dashed red curve is the locus of all circular orbits for all values of angular momentum. The orange horizontal line segment represents a specific elliptical orbit, this elliptical orbit, for this particular value of angular momentum. At infinite separation, the gravitational potential energy is 0. At finite separation, the gravitational potential energies for all closed orbits are negative. Because the force is attractive, the negative potential energy is a binding energy. The orange horizontal line segment, representing the orange elliptical orbit, has the same angular momentum as for the red dot, but more energy, less negative. And therefore it has a larger semi-major axis. The semi-major axis for the orange ellipse is longer than the radius of the red circle. The orange line segment intersects the green curve at 2 turning points. The left one is our min of the ellipse, and the right one is our max of the ellipse. Here is our min, here is our max, on opposite sides of the massive object, which is at the origin, which is the focus of the ellipse. Let's take some radial distance between our min and our max for this ellipse. If we subtract the green curve effective potential energy from the orange line segment total energy, we get a positive energy that is the radial kinetic energy for the orbit at that radial distance. This radial kinetic energy is 0 at the turning points. So at this turning point, which is here, if this were around the sun, this would be perihelion. At that point, the radial kinetic energy is 0 at the turning point. As we go from left to right, and we look at the radial kinetic energy, that corresponds to going here. The radial kinetic energy is 0 because it's at a minimum. But here there is some radial kinetic energy, and here we're going outward. We're going outward. Now we're still going outward. Once we get to here, we're at the maximum, and the radial kinetic energy is 0, and then we're going to come back toward the minimum. For Newtonian mechanics and two bodies, all of the elliptical and circular orbits are stable, and circular orbits are possible very close to the surface of the more massive object, ignoring friction from the atmosphere. These will not be true for general relativity and black holes, and they're also not completely true when we add more orbiting objects in Newtonian mechanics. Orbital maneuvers. Orbital maneuvers to change orbits are complicated. We will only consider the simplest case of applying a short duration of tangential rocket thrust while the radial distance is unchanging. So, at minimum or maximum distance in an elliptical orbit or in a circular orbit. We're not going to do the analysis, we're just going to quote the results. Applying positive thrust to increase the tangential velocity at an extremal point increases angular momentum, energy, making it less negative, and the semi-major axis. A circular orbit becomes a longer ellipse with the rocket starting at the minimum distance. For orbiting the Earth, this is perigee. For orbiting the Sun, this is perihelion. So, say we're in the orange orbit, orbiting the Earth, and we have a certain velocity here, and then we apply thrust to increase that velocity. We would shift from the orange circle to the green ellipse, and we would be at the perigee of the green ellipse while we were doing our rocket thrust. Applying positive thrust at perigee of an ellipse produces a longer ellipse. Applying positive thrust at the furthest point of an ellipse here, apogee or aphelion, it increases the semi-major axis, resulting in a longer ellipse or a circle. So if we were to increase our velocity at this point, we would have a longer ellipse or possibly a circle. Let's look at a simplified example, boosting from low Earth orbit, the orange circle, to geostationary orbit, the blue circle. First, from the orange circle, we apply positive thrust to increase our velocity, black arrow, to boost to the green ellipse, and we follow that ellipse from perigee to apogee. This thrust is called the perigee burn. It caused us to increase our angular momentum, our energy, and the semi-major axis. Second, at green apogee, we apply the second positive thrust to increase our velocity, again, our black arrow, to boost to the blue circle. This is called the apogee burn or apogee kick. We increased our angular momentum, energy, and semi-major axis. Now, beware of one common potential confusion. Earlier in the main course, we learned that for circular orbits, velocity decreases with orbital radius. So, the velocity of the blue circle is smaller than the velocity of the orange circle. We started out with the velocity in the orange circle, and we applied two positive tangential thrusts here and here. Shouldn't the final velocity in the blue circular orbit be higher than the initial velocity in the orange orbit? If not, why not? Well, the velocity at the green perigee was higher than the orange circular orbit, but the velocity decreased as we went from perigee to apogee according to Kepler's law. The second thrust increased the velocity above the green apogee velocity, but it remained less than the orange circular velocity, and we end up in agreement with the circular orbit velocity formula. Now, applying negative thrust to decrease tangential velocity at an extremal point decreases the angular momentum, the energy, and the semi-major axis. So if we're in the green orbit and we apply negative thrust here at perigee, it'll produce a shorter ellipse or a circle like this orange circle. But if we were in a circular orbit to begin with and we applied negative thrust, we would end up in a shorter ellipse with the rocket starting at the maximum distance, apogee, aphelion. If we apply negative thrust at the furthest point of an ellipse, apogee or aphelion, it will decrease the semi-major axis, resulting in a shorter ellipse. So if we were here and we applied negative thrust, we could be in that shorter ellipse. Hohmann transfer orbits are low-energy orbital maneuvers to transfer from one orbit to another using two thrusts of relatively short duration, with the possibility of a shorter mid-course correction burn that we will not discuss. We will consider the Hohmann transfer orbit to take a spacecraft from low Earth orbit to low orbit around Mars. We'll make the simplifying assumptions that Earth's and Mars's orbits around the Sun are circular and in the same plane as one another in the spacecraft's orbits. The spacecraft starts out in low Earth orbit. Here's the Earth, so the spacecraft is orbiting in this direction, counterclockwise, around the Earth. We're not really showing its orbit around the Earth. At the moment when the spacecraft is on the opposite side of the Earth from the Sun, so when it's on the left side here, we apply enough positive thrust to enter a particular elliptical orbit around the Sun, the red dashed orbit. In doing so, we escape the Earth's orbit. We choose the particular value of thrust to give us the elliptical orbit with a perihelion, closest approach to the Sun, equaling the Earth's orbit, and an aphelion, the furthest distance from the Sun, equaling Mars's orbit. This is the dashed red orbit. The semi-major axis of the elliptical transfer orbit is half the sum of the Earth's and Mars's elliptical orbital radii, so 1.26 AU. Once it gets some distance from the Earth, the spacecraft is freely orbiting the Sun, and we can use Kepler's law around the Sun, and we find that the period of the transfer orbit is about 1.4 years. The spacecraft will be tangent to Mars's orbit at aphelion in half of that time, half a period, so about 0.7 years or 8.5 months. But will Mars be where the spacecraft needs it to be to enter orbit of Mars? For the Hohmann transfer orbit from Earth to Mars, the launch window occurs every 26 months. We must plan in advance carefully. In order to meet up with Mars at the blue dot, Mars needs to be there when we leave Earth orbit, and that only happens every 26 months. So we cannot easily go to Mars whenever we please. We cannot leave when we please. We cannot arrive when we please. When the spacecraft reaches aphelion, we would apply positive thrust if we wanted to end up in Mars's orbit around the Sun without Mars being there. But to enter the orbit of Mars when Mars is there, we need to apply a negative burn to reduce our velocity to produce an elliptical or circular orbit around Mars. Here is a nice GIF showing the Hohmann transfer orbit from Earth to Mars. Earth is blue, purple is the spacecraft, green is Mars. To actually go to Mars, we need to account for the actual elliptical orbits of Earth and Mars, and that they're not exactly in the same plane. The Moon orbits about 60 Earth radii from the center of the Earth. The Hohmann transfer orbit from low Earth orbit to the Moon takes about 5 days. Launch windows occur 1 day per month, but some launch windows are less than an hour in duration. The solar system is more than one body orbiting the Sun. There are 8 planets. There are dwarf planets, asteroids, and comets. The 8 planets' orbits are elliptical orbits whose orbital elements change slowly over time due to perturbation by the gravitational attraction of the other planets. And comet orbits can be greatly changed if their orbit brings them close to Jupiter. Although all the parameters of a planet's orbit change slowly over time, there is one element that you are more likely to read about than the others. This is precession of the perihelion, the closest point to the Sun. This is an illustration of the precession, rotation, of the perihelia, blue dots, closest approaches of an orbit due to perturbations of other planets or of general relativity. The precession shown, the amount between the blue dots, is about 40,000 times Mercury's precession. And also the aphelion, the far distance, is too much. But it's a good diagram for showing you what the perihelion is and the direction in which it moves. If there were only a single body in the solar system beside the Sun, Newtonian mechanics predicts an ellipse whose parameters never change. The closest point of approach would remain unchanged forever. However, the existence of the other planets causes the perihelion to advance slowly over time. The major axis of the ellipse precesses, rotates around the focus of the ellipse, the Sun. The effect is largest for Saturn and Mars, being close to massive Jupiter. However, it's the precession of the perihelion of Mercury that gets the attention. Mercury's perihelion precesses 5.75 arcseconds per year. This means that the major axis makes a full rotation in about 225,000 years. In the 1700s and 1800s, astronomers calculated the contributions from the other planets and got 92% of the experimentally observed value. Pretty good, but that was as close as they could get, no matter how they tried. The remainder was called the anomalous precession of the perihelion of Mercury. It turns out that the anomalous precession is almost completely due to general relativity's curvature of space-time. Newton's 1/r² force law is not quite correct. When Einstein developed general relativity, he calculated the general relativity value for the anomalous precession of Mercury's perihelion, and it was correct. The general relativity correction is highest for Mercury, being closest to the Sun, higher than for the other planets, which is why you will hear about the precession of Mercury's perihelion, not the other planets. You can find many sources showing the math of the general relativity 8% correction to Mercury's perihelion precession, but it's much more difficult to find sources taking you through the 92% due to the other planets that the scientists in the 1700s and 1800s calculated. You might be surprised to learn that the planets' distances to the Sun changed quite a bit in the early life of the solar system. We will not cover gravity assist and gravitational slingshot in this course.